So, welcome to another very exciting session of healthcare entrepreneurship. So far, we have completed the conception module where we looked at how to generate the ideas from the current healthcare space and what is the scenario currently in India, as well as we have looked at how to generate the right ideas, what are the key steps for generating the right idea. We have talked about customer discovery, which is one of the very principal things to be conducted in order to understand who your customers are, and that forms one of the very important elements of the conception stage. We have also talked about the different stages of product development. So now we are slowly moving from the conception module to the design module. We would be learning more and more about how to design products and services. So today I'm going to talk about the first set of lectures in this module, which is on the topic is tools for design of products. So we wanted to learn about all the possible tools which are out there, what we can use for designing our next product or the medical product which we are planning to do, right? So let's get started. All right, so before we jump into the tools, let us talk about what is a design, right? So design, as per definition, is a plan or specification for the construction of an object or system for the implementation of an activity or process, or the result of that plan or specification in the form of a prototype, product or process. So what this typically long sentence means is basically design provides the specifications, and we have talked about product specifications and features if you remember from our previous lecture. So design basically gives all the dimensions, the key specifications, what are the details of a certain product, and this is helpful for conveying the same for the further implementation, which is actually the development of a prototype or the final product which comes into form in a three-dimensional setting. So design typically started with 2 dimensions and then moved towards 3 dimensions. So we are going to talk about some of the key aspects of the designs, right? So the first example here is of a classic hip implant. So typically what happens is whenever there is a hip failure or a hip fracture, usually happens at an older age and with persons having high degrees of arthritis, so specifically osteoarthritis, which is basically where the bone density keeps on reducing over time. This is a disease which has not found too much of cure. So basically, if your bone density reduces over time, then your hip joint is one of the key load bearers of the human body, right? And if you have put on a lot of weight, then basically there is a high chance of hip failure, because the hip is not strong enough. It has lost its bone density and the strength basically. So typically it doesn't happen while you're standing or just walking around. It typically happens out of an accident or there is a fall. So whenever that happens, there is a hip failure. It could be from partial to a complete hip failure. And the hip joint basically has the pelvic bone acting as a socket, and then there is a ball joint which is part of the femoral bone. So if you are looking at the figure at the right, on the right side of the pelvic bone, so you are looking at the pelvic bone and then the right side where there is a natural ball joint, and this is known as a ball and socket mechanism, right? However, on the left side you are seeing an implant which just replaces the function of that ball joint, ball and socket mechanism. But you could imagine well that how painful and traumatic the process would be, first of all, to surgically implant such a device, like which is this implant specifically, and also if there is a further failure or there's some kind of a design issue, then how difficult would that be to even repair it, right? So keeping that in context, so typically what is done is you have this longest bone on the body which is known as the femur. So within the femur it is drilled and initially, and then the hip implant is placed in, and then it is kind of surgically left to absorb itself or like integrate, osseointegrate with the surrounding bone, and basically then it kind of replaces the function of the femoral bone eventually, right? So this implant has several components, including the femoral stem, which has a specific type of contouring or the surface texture, as well as the material could be different. So, the idea here is basically you want to enhance bone growth. So, because you have drilled inside the bone, placed an implant, one is you want to maintain biocompatibility, which is that the body is not rejecting the implant. Second is you want to enhance bone growth, right. So, if both these things are done right, then you have the other parts of the implant, which is the femoral head, which has to be able to support your entire body load, at least the half of the entire body load, because you're on both feet. And then there is this plastic liner and acetabular component, which is the topmost component, which is in contact with the pelvic socket basically. Right. So, coming back to the design, there needs to be very specific design parameters, and in majority of the cases there would be some standard implants which are off the shelf, and most of these design parameters have already been kind of derived from literature and previous cadaveric studies and clinical studies. But few of these implants would be requiring to be customized in cases where there is a very specific case of hip failure or deformity, right. So, the things to notice here are, we are looking from the lengths, the breadths, then we are looking at radiuses like fillets, all the small little details wherever there is a design component change which is deviating from a simple line, that has to be addressed. Typically a design is kind of looked upon from at least 3 directions. It's just 2 directions which is presented here, but typically we would like to see a side view, a front view and a top view, and have all the dimensions there, because that is the only way we can fully have the dimensions defined in a 3-dimensional space, right. And then we can take this design to further modeling, right. So, that's what a design usually is. It has a specifications with all the dimensions and details. So, let us look at some of the traditional designs, how they were being done. So, there are 2 types of traditional designs. Back in the day, what they would like to do is, there was usually this graph paper. Many of us would have used it in schools and colleges. Like we take this graph paper, and basically that has specific intervals, and we can clearly draw from here to here using a compass or a ruler, and you could use everything in your geometry box to basically construct all the previous traditional designs. So, back in the day when softwares were not around till maybe 95 or early 2000s, when it was not very commercialized, most of the designs were done by hand. So, very specifically not only the healthcare designs, but also civil engineering and very complex mechanical designs. So, they were typically done by hands. So, under the traditional designs there are 2 types. First is design without dimensions. So, you are looking at an screw kind of implant. This could be some form of dental implant. So, this is typically defined by a certain edge length and spacing, and there is a thing called pitch, which is basically the difference between, or the spacing between the 2 helical threads, like which is going from top to bottom or bottom to top. Then you have different views to take a look at it. But why is it without dimensions? So, this is typically the kind of design which you will see in a patent document or an intellectual property document. So, just most of this document being public information, you do not want to divulge the exact dimensions of your design or product design, right. So, majority of the designs, if you are filing a patent or you are reading up a patent, will be like this: design without dimensions. Sometimes they would be scaled in a certain way so that somebody cannot copy this at all. You will be very surprised to believe that many companies and folks out there are actually trying to copy several patent designs. What they would do is, sometimes if the dimensions are missing, they would try to trace it on a graph paper or some Photoshop based software and try to understand what the relative dimensions are, like given this some kind of a scenario. So, in order to avoid that, many of the patents have different scaling, where it is very difficult to know exactly what the relative dimensions are or what the specific dimensions are, right. So, these are usually designs without dimensions. Then you have designs with dimensions. That's the common one. So, here you are looking at another screw base implant with a very detailed dimensioning, right. You are looking at dimensions of the length, wherever there is a slight change in the contour from different directions as well. If you are seeing from the bottom, if you are seeing from the top, the features are different. So, every small little detail is dimensioned, every fillet, every curvature, every length, right. Wherever the design is changing, that is kind of dimension. So, you could think of like just looking at the clutter designs on the right, how difficult it may be to really work on these designs, right. It is very easy to think from a perspective that of a value proposition or trying to understand what the customers perceive, like sometimes then working on the technicalities. So, therefore, like one of the common things which happens is the customer discovery and other things take the back seat, and most of the entrepreneurs focus on the designs and development aspect, but that's a fallacy. That's something which is going to lead to a startup failure, which I've already been talking about in the previous lectures. So, design is also an important aspect, but do not have to really stress about it. It may look very cluttered, but most of the softwares are there these days to take your design further, right. So, these are some of the examples. Let's go next. So, what are some of the design tools and 3D modeling softwares out there? So, one of the very popular 3D modeling software is SolidWorks. This is primarily if you are from a mechanical or any sort of engineering background, you would have come across SolidWorks. Very heavy software, so unless and until you have a computer or laptop which is of a good amount of RAM memory, it may not run that fine. SolidWorks is a 3D modeling software where you can also build sketches and kind of then form 3D structures, as well as you can work with assemblies. So, you can have a product with multiple components, like so we work with medical devices which is 3000 odd parts or 300 odd parts, and you can basically create all those parts separately and put them together in order to form an assembly, which is your final product, right. So, SolidWorks allows you to do that. The other softwares out there are CATIA, for example. This is also from the same company, Dassault Systèmes. So, typically what's the difference between CATIA and the SolidWorks? So, CATIA is kind of an adapted version of AutoCAD. AutoCAD used to be one of the oldest kind of CAD softwares, where usually it would be used for drafting and all the 2D sketches and designs. So, typically you could add dimensions to 2D sketches and kind of then have them together in form of 2D drawings. So, that was what typically AutoCAD was. A higher version of AutoCAD was basically CATIA, where you can convert these sketches and designs to basically 3D models, right. So, I think the latest version of CATIA, I have not used it in the past maybe 10-15 years or so, like it has evolved over time. So, CATIA may be using quite a bit of the AutoCAD features together, and probably is able to work very similarly to SolidWorks. But SolidWorks is something which we find very simple. It's very easy to learn. There are a lot of tutorials and videos out there online. I can mention those list of links in one of the upcoming lectures, and you are able to like put this as a tutorial and learn about it more. The other companies which are also there as competitors for 3D modeling softwares include the Siemens NX, Autodesk Fusion 360, Creo. Creo is very popularly used for automotive manufacturers, by them for designing the different vehicular parts and car components and whatnot. It is also used for toy manufacturing. So, lots of this toys which children play with, Creo is quite popular in that arena. Like these are certain features which are very unique and quickly lets you give some adaptive control, where there are certain designs which they can mention these are the some possible design iterations, and you can select few of these. So, little bit better adaptation there. But typically what we have seen is SolidWorks is the most popular across the industry, right. So, with this we are going to close this session. We will continue this topic in the next lecture. So, thank you all.